So let me just show you how to. So before I do any of that, the first thing I want to show you is the idea of like terms, because that's how you add and subtract polynomials. So two terms are like terms if they have the same variables to the same powers. Now, notice that there's no requirement about the coefficient. So, for instance, that is a weird p. Anyway, we're just gonna go right by that p there. So, for instance, 3x to the fourth and 7x to the fourth. Those are like terms. Notice that each one is a term, and they have the same variables to the same powers. Similarly, negative 2.5a squared b to the third is like terms with 7.1a squared b to the third. I guess I like sevens here. So those guys are like terms because they have the same variables to the same powers. And then something like, let's say, 2x to the fifth and 2x to the fourth, those are not like terms. So let's just go ahead and, those are not like terms. They have the same variables, but to different powers. And you can have the same powers, but different variables, of course, and that would be not like terms. So if you have like y to the third z and 2y z to the third, those are not like terms either because they have the same variables, but different powers on the variables, even though it's a 3 and a 1 still. So those guys are not like terms either. So why do I care about this? The reason I care about like terms is that I can sum up adding and subtracting polynomials by saying combine like terms. That's it. That's how you do it. There's literally nothing else to it. So if I have two polynomials, let's say I have, I'll start out easy, 2x to the fourth plus 3x minus 1, and I want to add, so there's one polynomial, and I want to add 7x to the third minus 5x plus 2. What I'm going to do is I'm going to combine like terms. All the terms that are alike get their coefficients combined, and all the ones that don't. So here I've got 2x to the fourth, 7x to the third. So what I'm looking for is I'm looking for anything that has the same powers, any terms that are like terms, right? And so I've got these guys are like terms, these guys are like terms, and the other ones aren't, right? There's nothing else with a fourth power, and there's nothing else with a third power. So 3x minus 5x is minus 2x. Minus 1 plus 2 is plus 1. So when I want to add these up, when I want to add these polynomials up, that's literally all I'm going to do. I'm going to write all the terms out with the like terms combined. So this is going to be 2x to the fourth plus 3x minus 5x is minus 2x. Oops, sorry, I'm doing that out of order for some reason. I don't know why. So I started with fourth power. I want to go down to the next power. The next power down is a third power, not first. I jumped the gun there. So it was plus 7x to the third is the next thing I want here. Plus 3x minus 5x is minus 2x. So I got minus 2x. And minus 1 plus 2 is plus 1. So there you go. That's it. That's how you add polynomials. You just combine the like terms. It's also how you subtract polynomials, which is nice. So the way I'm going to subtract two polynomials here. So let's say I have x squared plus 3x minus 5 minus 2x squared minus x plus 1. So what I'm going to do is literally the exact same thing, except I'm also going to distribute this minus sign to everything that it goes to. Right? Remember that minus signs are on the thing that they're in front of, not the thing that they're behind. So I'm just going to distribute the minus sign here and then combine like terms. That's it. That's all I'm doing. X squared plus 3x minus 5. So that stays the same. Then I've got minus 2x squared plus x minus 1. So notice that minus sign went on everything here. And then I combine like terms. So I get minus x squared, I get x squared minus 2x squared. Then I got plus 3x plus x is plus 4x. I've got minus 5 minus 1 is minus 6. And there really is nothing else to adding and subtracting polynomials. Yeah, that is in fact all there is to it. Let me show you one kind of notation example. So let's say I have like p of x equals 2x minus 3, and q of x equals minus x to the third plus x minus 5. Right, so I'm going to call my polynomial something this time. Well, I can do p of x plus q of x. And that'll just be 2x minus 3 plus negative x cubed plus x minus 5. You can also write this as p plus q of x. That's another really common way to write this. I'll generally stick to the first one, but this is totally fine as well. This does not mean distributed. This is just a function called p plus q, or a polynomial called p plus q, whose variable is x. But this is not multiplication. Don't think of like distributing the x, even though it kind of looks like it. So this is 2x minus 3 plus a negative x cubed plus x minus 5, which is, well, we're going to combine like terms here. So my biggest power is x cubed. Next biggest power is x's. So I have 2x plus x is plus 3x. And then I got the constants. So I got minus 3 minus 5 is minus 8. And of course, I can do p of x minus q of x as well. Same thing, but distribute the minus sign. And that's adding and subtracting polynomials. That really is all there is to it. Sometimes there'll be fractions or decimals or whatever, but just add normally. Just add and subtract normally. And yeah, like if you're being super pedantic about it, you could say that just saying combine like terms is enough information to add and subtract polynomials. That literally is everything there is to it. All right, let me talk about how to multiply polynomials. So multiplying polynomials is a little bit different. It is a lot of distributive property. So for instance, let's say I have this. Let's say I have 2x. That is a polynomial. It's a monomial, but a monomial is a kind of polynomial, times let's say x squared minus 5. So what I'm going to do is I'm going to take this and distribute it to everything. So 2x times x squared is 2x cubed. 2x times negative 5 is minus 10x. So we're just using rules of exponents here, right? The stuff we did in rules of exponents. Yeah, and that's how you do that. That really is all there is to it, to just distribute. Now, this gets a little bit more complicated when both polynomials have more than one term. So if I have something like this, minus 7, let's make a 2 there. Then not only does, say, the 5 have to go to both things, but the x has to go to both things as well. So when you're multiplying polynomials, the trick is everything gets multiplied by everything else. Every term in one gets multiplied by every term in the other. So the easiest way to do this is just one at a time. So despite the way I wrote this, I'm going to do the x's first. What I'm going to do is I'm just going to distribute everything in the first polynomial one at a time. So I'm going to start by distributing the x to everything. Then I'm going to distribute the 5 to everything. And then I'm going to combine like terms. And I'm going to specifically arrange these in such a way that like terms are in columns. I'll show you what I mean. So when I do x times 2x, I get 2x squared. X times negative 7 minus 7x. 5 here, I suppose I should, here, let me redo this. Right, so what I did there was I did x times 2x and then x times negative 7. And now I'm going to do 5 times 2x and get 10x, and I'm going to put that here. Right, that's a plus 10x. And I'm deliberately arranging it under the other x so that I can just add straight down in a second. Oop. Like that. Now, when I have two binomials that I'm multiplying, this is it's probably not necessary to do it, right? I could have just, done minus 7x plus 10x minus 35 all in one line. Would have been fine. This gets much more helpful the bigger your polynomials get. So for instance, let's do a pretty hefty example. So let's say I have this t squared minus 2t plus 1 times 3t squared plus 5t minus 3. This is going to be a bit of a mess. Now notice we're going to have 9 terms. So I'm going to have 3 terms from distributing the t squared, and 3 terms from distributing the minus 2t, and 3 more terms from distributing the 1. And that's going to give me 9, which is kind of a lot to keep track of, to be honest. Like this does actually get pretty messy. So arranging these in columns really helps. So let's do that. So I actually don't have room on that line, so we're going to start a new line. So I'm going to do t squared times 3t squared is 3t to the 4th plus 5t to the 3rd minus 3t squared. It's going to get too messy if I keep drawing the lines, so just know that I'm starting over with the negative 2t's now. So negative 2t times 3t squared is minus 6t to the 3rd minus 10t squared plus 6t, and then 3t squared. So now with the ones, 1 times 3t squared is 3t squared. I suppose that's a plus 5t minus 3. And so now you can see why it's helpful that I've arranged them in columns, right? Then obviously if we had 4 terms, this would just get bigger, and it's more helpful to arrange it in columns the more terms you end up with. So when I combine like terms here, I'm just going to add straight down, which is really nice. It's very much like place value. 3t to the 4th minus t to the 3rd minus 10t squared plus 11t minus 3. There we go. So it's often the last step of combining all the like terms that people stumble in. So it really, really helps if you line them all up like this. Certainly don't have to. You can write it all out in one big chunk if you want to. I prefer to do it like this personally. And that's pretty much what multiplying polynomials is. So to multiply polynomials, you really want to just make sure that you are distributing everything to everything else is basically how it goes, right? So each term in your first polynomial that you're multiplying gets distributed to all the terms in the other one. Then you combine all the like terms. This has an acronym in this particular case where they're both binomials called FOIL, which you've probably heard before. I don't really love calling this foiling because like that doesn't apply to anything except 2 and 2. Right? If either of these is not a binomial, FOIL doesn't make sense. But by the way, if you haven't heard it before, FOIL stands for first, outer, inner, last. So that the idea there is that you're giving yourself an acronym to follow to make sure that you get all the things, or all the terms in the polynomials. The problem is if you try FOIL with anything except this, the acronym fails, and it's just not a great name. But so that it's for first, outer, inner, last. Notice I did the first terms and the outer terms and the inner terms and the last terms. Again, good for binomials, which are actually the most common ones that we multiply. However, FOIL only has 4 letters and there's 9 terms here. So you can imagine doing the first, outer, inner, and last here does not get you what you want. So just think of it as multiplying. It's multiplying and there's a lot of distributive property. And I believe that's really all I wanted to say about multiplying polynomials. There isn't a lot to it, or rather, there's not a lot to know. There's kind of a lot to do. It gets a little messy. But yeah, I think I will go ahead and leave you with that. So I will stop this video and I will see you guys in the next one.